हॅलो फ्रेंड्स, तर राणा अकॅडमी या यूट्यूब चॅनलवरती आपणा सर्वांचं स्वागत आहे. आपण स्टार्ट केले आहे 11th क्लासची केमिस्ट्री, ज्यामध्ये आपण 2 चॅप्टर कव्हरअप केले आतापर्यंत. आता आपण हे तिसरा चॅप्टर कव्हरअप करणार आहोत या व्हिडिओमध्ये. चला तर मग व्हिडिओला सुरुवात करूया. तुम्ही या चॅनलवरती नवीन आला असाल तर प्लीज या चॅनलला सबस्क्राईब करा आणि बेल आयकॉन हिट करा. चला तर मग व्हिडिओला सुरुवात करूया. थर्ड चॅप्टर आहे आपला क्लासिफिकेशन ऑफ एलिमेंट्स अँड पिरियॉडिसिटी अँड प्रॉपर्टीज. सम इम्पॉर्टंट पॉईंट्स. Dobereiner triads. In 1817, a German chemist Dobereiner identified certain groups of 3 elements. These groups of 3 elements having similar properties was called triads. When 3 elements were arranged in order of their increasing atomic masses, the atomic mass of the middle element was roughly the mean of the atomic masses of the other 2 elements. Newland's law of octaves. When elements were arranged in order of their increasing relative atomic masses, the properties of every 8 elements were similar to the first one, like the 8th note of a musical scale. This repetition in the properties of elements is just like a repetition of 8th node in an octave of music. Mendeleev's periodic law. The physical and chemical properties of elements are the periodic functions of their atomic masses. Next point, Mendeleev's periodic table. When Mendeleev started his work, 63 elements were known at that time. He selected hydrogen and oxygen as they were relative to and formed compounds with most elements. Mendeleev's periodic table contains vertical columns called groups and horizontal rows called periods. There were 7 periods and 8 groups. Noble gases were not known at that time. So there was no group of noble gases. The elements in each group of the periodic table are similar to one another in many properties. The similar properties of the elements are repeated periodically. Merits of Mendeleev's classification. Mendeleev's periodic law predicted the existence of some elements that had not been discovered at that time. Could predict the properties of several elements on the basis of their position in the periodic table. Could accommodate noble gases when they were discovered. Next point, limitations of Mendeleev's classification. The correct position could not be assigned to the hydrogen in the periodic table. Wrong order of the atomic masses of some elements could not be explained. The position of isotopes could not be explained. Uncertainty in prediction of new elements was there. Modern periodic law. Properties of elements are the periodic function of their atomic number. Modern periodic table. This table was prepared by Bohr and is based upon the electronic configuration of the elements. The table consists of 18 vertical columns called groups. Groups elements having similar outer electronic configurations in their atoms are arranged in vertical columns, referred to as groups, according to the recommendation of International Union of Pure and Applied Chemistry (IUPAC). The groups of numbered from 1 to 18 and the table consists of 7 horizontal rows called periods. The first period contains 2 elements. The subsequent period consists of 8, 8, 18, 18, 32 elements respectively. The 7th period is incomplete, and like the 6th period would have the theoretical maximum on the basis of quantum numbers of 32 elements. In this form, the periodic table 14 elements of both 6th and 7th periods, lanthanoids and actinoids respectively, are placed in separate panels at the bottom. Modern periodic table. Notation for IUPAC nomenclature of elements with Z is greater than 100 digit. Name abbreviation. Nil 0, un 1, by 2, 3, try 3, quad 4, pent 5, hex 6, sept 7, oct 8, un 9. We can easily the elements into our four blocks by Z, S block, P block, D block, F block, depending on the other types of atomic orbitals that are being filled with electrons. S block elements. The elements of group 1 alkali metals and group 2 alkaline earth metals, which have NS1 and NS2 outermost electronic configuration, belong to the S block elements. P block elements. The P block elements comprise those belonging to group 13 to group 18, and these together the S block elements are called representative elements or main group elements. The outermost electronic configuration varies from NS2 to NS2 and P1 to NS2 and P6 in each period. D block elements. These are the elements of groups 3 to 12 in the center of the periodic table. These are characterized by the filling of inner d orbitals by the electrons and are therefore referred to as d block elements. These elements have the general outer electronic configuration n-1, the d power minus 10, d power n 1 to 10, and ns 0 to 2. F block elements. Next point I apply F block elements. The two rows of elements at the bottom of the periodic table called the lanthanoids. C Z is equal to 58, Lu Z is equal to 71, and actinoids. Z is equal to 90 and Lr Z is equal to 103. Are to which are characterized by the outer electron configuration n minus 1 F power to the power 1 to 14, n minus 1 d to the power 1 0 to 1, ns2. The last electron added to each element is filled in F orbital. These two series of elements are hence called the inner transition elements. Next point is variation in atomic radius or in period. The atomic size generally decreases across the period. It is because within the period the outer electrons are in the same valence shell and effective nuclear charge increases as the atomic number increases, resulting in the increased attraction of electrons to the nucleus. Next number plus point है variation in atomic radius in group. Within a family or vertical columns of the periodic table, the atomic radius increases regularly with the atomic number as we descend the groups, and the periodic principal quantum number small n increases and the valence electrons are further from the nucleus. This happens because the inner energy level are filled with electrons which serve to shield the outer electrons from the pull of the nucleus. Consequently, the size of the atom increases as reflected in the atomic radii. The atomic radii of noble gases are not considered here, being monoatomic. They are non-bonded radii. Values are very large. In fact, radii of noble gases should be compared not with the covalent radii but with the van der Waals radii of the other elements. The cation is smaller than its parent atom because it has fewer elements, while its nuclear charge remains the same. The size of an atom will be larger than that of the parent atom because the addition of one or more electrons would result in increased repulsion among the electrons and the decrease in the effective nuclear charge. For example, the ionic radius of fluoride ion is 136 pm, whereas the atomic radius of fluorine is only 64 pm. On the other hand, the atomic radius of sodium is 186 pm compared to the ionic radius of 95 pm for sodium ion. Next point, isoelectronic species. Atoms and ions which contain the same number of electrons, for example O di negative, F negative, Na positive, Mg di positive, have the same number of electrons, 10. Their radii would be different because of their different nuclear charges. The cation with the greater positive charge will have a smaller radius because of the greater attraction of the electrons to the nucleus. Anion with the greater negative charge will have the larger radius. In this case, the net repulsion of the electrons will outweigh the nuclear charge and the ion will expand in size. Next point, ionization enthalpy. It represents the energy required to remove an electron from an isolated gaseous atoms in its ground state. In other words, the first ionization enthalpy for an element X is the enthalpy charge for the reaction depicted in equation. Xg gives X positive plus electrons. The ionization enthalpy is expressed in units now of kilojoule per mole. We can define the second ionization enthalpy as the energy required to remove the second most loosely bound electron. It is the energy required to carry out the reaction shown in the equation. The X plus then gives the X di positive plus electron. Energy is always required to remove electrons from an atom, and hence ionization enthalpies are always positive. Are always positive. The second ionization enthalpy will be higher than the first ionization enthalpy because it is more difficult to remove the electron from the positively charged ion than from the neutral atom. In the same way, the third ionization enthalpy will be higher than the second ionization and so on. The term ionization enthalpy is not, if not qualified, is taken as the first ionization enthalpy. Variation in ionization enthalpy is group in group. Next point आहे आपला variation in ionization enthalpy in group. As we descend in the group of first ionization enthalpy generally decreases because as we go down a group, the outermost electron being increasingly further from the nucleus, there is an increased shielding of the nuclear charge by the electrons in the inner levels. In this case, the increase in shielding outweigh the increasing nuclear charge, and the removal of the outermost electron requires less energy down a group. Variation in ionization enthalpy in period. The first ionization enthalpy generally increases as we go across a period. When we move from left to right in period, successive electrons are added in orbitals in the same principal quantum level, and the shielding of the nuclear charge by the inner core of electrons does not increase very much to compensate for the increased attraction of the electrons to the nucleus. Thus, across a period, increasing the nuclear charge outweighs the shielding. Consequently, the outermost electrons are held more and more tightly, and the ionization enthalpy increases across the period. Next point, electron gain enthalpy. When an electron is added to a neutral gaseous atom X and to convert it into the negative ion, the enthalpy change accompanying the process is identified as the electron gain enthalpy. Electron gain enthalpy provides a measure of the is with which an atom adds an electron now to form an ion has represented by equation x plus electron is gives x negative, and depending on the elements the processes of adding an electron to the atom can be either endothermic or exothermic. For many elements, energy is released when an electron is added to the atom, and the electron gain enthalpy is negative. For example, group 17 elements, the halogens have very high negative electron enthalpies because they can attain stable noble gas electronic configuration by picking up an electron. On the other hand, noble gases have large positive member of each group is 4. Example, boron can only form whereas the BF4, whereas the other members of the groups can expand their valence shell and to accommodate more than 4 pairs of electrons. Example, aluminium forms AlF6 tri-negative. Furthermore, the first number of p block elements displays greater ability to form p and multiple bonds to itself. Carbon carbon double bond, carbon carbon triple double bond, nitrogen nitrogen double bond, nitrogen nitrogen double bond, and two other second period elements: carbon oxygen double bond, carbon nitrogen double bond, carbon nitrogen double bond, nitrogen oxygen double bond compared to subsequent members of the same group. क्लासिफिकेशन ऑफ एलिमेंट्स अँड पिरियडिसिटी इन प्रॉपर्टीज हा चॅप्टर आपला इथे संपतो. आपण या चॅप्टरमध्ये पहिल्यापासून पाहिलं डोबरॅनस ट्रायड्स पाहिले, त्यानंतर न्यूलँड्स लॉ ऑफ ऑक्टिव्स, मेंडेलिव्हज पिरियडिक लॉ, मेंडेलिव्हज पिरियडिक टेबल, मेरिट्स ऑफ मेंडेलिव्हज क्लासिफिकेशन, लिमिटेशन्स ऑफ मेंडेलिव्हज क्लासिफिकेशन, मॉडर्न पिरियडिक लॉ, मॉडर्न पिरियडिक टेबल, एस ब्लॉक, पी ब्लॉक, डी ब्लॉक, एफ ब्लॉक एलिमेंट्स, variation in atomic radius in the periods, variation in atomic radius in groups, isoelectric electronic spaces, ionization enthalpy, इलेक्ट्रॉन गेन एन्थाल्पी, आणि हा इथे आपला चॅप्टर संपतो. तर तुम्ही या चॅनलवरती जर नवीन आला असाल तर प्लीज या चॅनलला सबस्क्राईब करून ठेवा, जेणेकरून आमचे नवीन नवीन व्हिडिओज तुमच्यापर्यंत पोहोचतील. प्लीज लाईक शेअर अँड सबस्क्राईब. थँक्यू सो मच फॉर वॉचिंग.